And the light is blinking. So 26, chapter 26, problem 51. All right, so we have the potential is some constant, e to the negative AR over R. A is positive. So it comes down to the relationship between the electric field and the electric potential. In general, it's equal to the negative gradient of the potential, and that's supposed to be a nabla there. But we have only one variable here, the radius, and so we can simplify it down into negative del V del R. Or I guess since we have only one variable here, negative dV dr R hat. So it's just basically doing a derivative with respect to the radius, or the distance there. So I have two functions, I have two terms, factors, that's the word I'm looking for. Two factors here which are dependent upon R. And so we'll be doing the product rule. So V sub naught e to the negative AR, R to the negative first. I just find this easier personally. So the derivative with respect to R, well, we do the derivative of the first one, negative A e to the negative AR, that's R to the negative 1, plus V sub naught e to the negative AR times negative R to the negative 2. Not a pretty form, but we can simplify it from there, but that's the essence of it. We have V naught that is constant. We have e to the negative AR, which is common, so we've taken care of that and that. And I'm left with AR to the negative 1 minus R to the negative 2. We pull an R out, so the V naught e to the negative AR over R, A minus 1 over R.
It's minus A minus 1.
Oh. So I can factor the negative out. Is that corrected? Okay. And they're asking for the R hat.
Since they're looking for the negative gradient, won't the negative also cancel?
Oh, all these little mistakes. It's a good thing none of you do this. Any other silly errors? I was so focused on the cool part, the calculus, that I lost track of the little stuff. And then ultimately they wanted determine the magnitude of the electric field. Well, they didn't give us a particular place here, so the magnitude would just be this right here. That's the magnitude. Was something there that sort of messed you up, or?
Yeah, the gradient part.
Ah.
But it seems simple enough.
Except for the stupid minus signs. Let's just do one other check here. So R, assuming that we have some central point, as R increases, my potential gets smaller, and the electric field points in the direction of the decreasing electric potential. Just make sure that's right, because positive. Yeah. So the electric field is pointing away from R hat. So the bigger R gets, oh, wait a second. I'm gonna have to trust that that works. No, it's still pointing outwards. This is a positive number right here. The electric field points away, and the electric potential gets smaller the farther out you go, which is the way it's supposed to work. Other questions?
Can you do number 80?
80?
Yeah.
All right, so electric potential at the point there. There's an eraser somewhere. Ah, there it is. All right, so this is 75 or 0.75 meters from here to here. Point P. This is 0.25 meters. This is 0.75 meters. The linear density is 2.25 nanocoulombs per meter. Find the electric potential here. All right, so electric potential doesn't really care about direction. And so if I can figure out the electric potential from this section, it's going to be the same as this section. So I'll get something valued for here, double it, and then I'll do it for the semicircle. So I picked some little portion right here, some dq, big Q, little q, whatever is your mood at the moment. And I know that the differential of my potential from the section 1, so I'm just putting a little 1 right here. This is section 1 to, in essence, 1. This will be equal to K dq over R. And so the potential at point P from this section over here is going to be the integral of dq over R. I have two variables here. I have Q is a variable because it's part of my differential, and R is a variable because the distance from P to this little section right here is going to vary along this line right here. So let's get it in terms of a single variable. I know that lambda, I believe it's uniform linear density, or they just said linear density. Uniform charge per unit length. So that dq, the length, what do we call it, x? X. And let's make x equal 0 here. So dq is just lambda dx. R is the distance from here to here, and since I've declared x to be 0 here and positive to my right, this distance here is x. So I know that R, the distance from point P to my infinitesimally small bit of charge, plus x has got to be equal to 1. That is the distance from here to here. So R is equal to 1 minus x. So this now becomes our electrostatic constant times lambda dx over 1 minus x. I now have a single variable. Let's do some limits of integration. Well, the smallest value of x is 0, and the largest value of x is 0.75. That is an x there. Lambda is a constant, so it will pull out. And so I got k lambda integral of dx over 1 minus x, which is k lambda negative natural log of 1 minus x from 0 to 0.75. I did. Pardon?
That was -1 to -0.25, and then flipped around 0.25 to 1. Because you only care about the charge coming from the distance away from the point, which is 0.25 away from that point.
Oh, from here to here?
Yeah, because the radius.
Right, but when I expressed everything in terms of x, it's different because x is going from here.
Oh, I see.
Instead of defining x, instead of defining in terms of r, I did it in terms of x.
Okay,
So that's the difference there.
makes sense.
And so we can actually get a number of 9 times 10 to the 9th times 2.25 times 10 to the negative 9th times the natural log of 0.25 oh, I lost my minus sign up there. So this will end up being a negative number, and then that negative right there, the one that comes from here, will cancel out with it. And you get something just spectacular that will make the world a better place. And then we've got, so whatever number we have there, we'll double it again because we got this side over here. Now we have this part, which is actually the simplest part. We can do it the long way. And what the heck, let's do it the long way. Actually, before I do the hump, any questions? Any other questions? Lawson?
Can you explain one more time why the intervals of integration are 0 to 0.75?
Because I made x my variable.
So x only goes to 0.75?
Yeah, because I said x was equal to 0 at this point right here. And so the smallest value of x along this line, this is basically where my charge is 0. My largest is 0.75 because that's as far away as it goes.
Okay, so you only care about 0 to 0.75 because that's where the charge is.
Right.
Okay.
If I had chosen r as my variable instead of x, then r would have gone from 0.25 to 1.
Okay.
And yeah.
It kind of does that when you plug it into the formula though. 1 minus x, 1 minus x, and then you get 0.25 and 1 in the natural log function.
Yeah. The great thing about math, you can do it more than one way and get the same answer. Despite what your experience might be on a test. Other questions? Lawson, did I answer your question?
Yeah.
Okay. All right, besides that one, any other questions? All right, so the circle here, or semicircle, I have again some differential dq. Let's just come up with some temporary variable, theta. And again, it has to be temporary because theta is not mentioned in the problem at all, so this is something I'm bringing into it. And again, we're left with k dq over r. And I can actually write that neater. V2 is integral of k dq over r. Well, k is constant, so it pops out. R is constant because it's the same distance no matter where you are, so that's constant, so I'm left with k over r integral of dq. And if I have the integral of just a differential, well, it's just that letter q, it's the charge along that semicircle, which is k over r times q. Although it feels like it should be a big Q at this point. If you can make the code switch there from little q to big Q.
Wouldn't you define it like lambda is equal to dq over ds, because it's the arc length, and then you do dq is equal to lambda times ds, and lambda stays constant, so you take the integral of the arc length.
You can do it that way too, no problem. I was just gonna make the substitution at this point.
Oh, okay.
And so it would be lambda times half of a circumference, so pi r. So this is k lambda pi, which is some number again that will rock your world. And so whatever this is, you got two of them plus this. Questions on this masterpiece? Okay, other questions?
Yeah, I do have a question. So, could you explain why it's r plus x equals 1? Because it's gone from the dq right there to the p, right there, that r at the bottom of here. Like, yeah, where you pointed.
Right, so I got dq here.
Yes, that's x. And then the r is from there to p, right?
R technically is from P, yeah, R is that distance there.
Okay.
Right, it's not directional, it's that distance.
Yeah. Okay. Okay, I get it.
Does it bother you that, are,
No.
going back to Mario's thing, are you bothered by the limits of integration?
No, I was
Okay.
just a little lost for where you're asking.
You're bothered by the fact that there's just a lot of clutter there? Yes, add more clutter, that usually clears it up. It's like my problem with writing labs. People have an issue with one spot, so I add more words. More words that people won't read. All right. In absence of other questions, let's take care of this other part. Make sure I'm not handing out the one that was half printed. All right. Okay. This problem's not on there, but there's something similar to it, which would give an advantage to the people who got the quiz first, and versus the people who got it later. I guess we got a test in a week and 2 days, so any questions from chapters 23 through 26? I'm about to come up with a question.
I do have a question.
Okay?
Let me just- So it's about, electric potential. I think it's more of a theoretical or conceptual question.
Okay?
Um, So when you release an electron from rest in a uniform external electric field,
Right?
so I know that the electric potential energy of the system will decrease because the kinetic energy will increase.
Well, let's open that up to the class. Why, if you release the electron and it starts to move, I guess it's bathed in an external electric field, it will start to move. Kinetic energy will indeed increase because it starts to rest and then starts to move. Why does that mean the potential energy will decrease?
Law of conservation of energy.
Why does that apply here?
Because as kinetic energy is increasing, you have to, the potential energy has to counteract that to maintain that conservation of energy.
That doesn't explain why. I can take this off, this pin right here,
It's a conservative force.
that's the key right there. Because I can take a pin right here and increase its potential, increase its kinetic energy, but it did not do anything to its potential energy. Because I'm non-conservative force. Yeah, the key is that it's conservative force involved.
So for electric potential, at the initial location of the electron, will that change or will that change because the electron is also kind of influencing the electric potential at that point, so when it leaves, it kind of,
It's now influencing that spot.
so that means it decreases?
So, if we think of an electron as a sphere, just a tiny one. There's some electric potential at the side right here, and it should be, like, if we're assuming some sort of conducting type surface, it should, yeah, it depends on how you want to model the electron, but, there's some potential at this spot right here, it moves, and so it is exerting a potential right here. The farther away it gets, the less negative it is. So actually it would increase the potential because it becomes less negative.
Oh,
Make sure I didn't throw an extra negative sign in there. Because if it definitely goes from here, so this has some, say, negative 10 volts, and then when it is here, it is farther away, so it would be a smaller negative number. So that is an increase.
I see.
All right, other questions?
Well, how can we tell whether electric potential energy at a point is a local minimum or a local maximum?
Stable versus unstable. All right, so that was the stable versus unstable, or was that a separate?
No, it was just justify conceptually or mathematically.
All right, so in terms of local minimum or local maximum, if we think about a bowl with a ball on top of it, or a bowl with a ball at the bottom of it, and there's basically two ways. If I push the ball a little bit, it's going to come back into it. This would be a local minimum. local maximum, if I give it a push, the thing is just gonna keep going. So conceptually, that's what we're talking about here. So if you have the formula for potential energy in terms of presumably R, be my guess, so as a function of R, mathematically, you take the second derivative with respect to R, it's like blanking here, so you do the second derivative, you want to see, oh no, take the first derivative, set that equal to 0, solve for R, and then that will tell you where the minimum is, and then take the second derivative, plug that value of R in there, and if it is positive, then that's a local minimum. If it's negative, it's a local maximum. So that's the mathematical way of doing it. From a conceptual point of view, it's, if I give it a slight touch, sort of think about which way the forces are acting on it. If I give it a small little push, is it gonna be forced back to where it was, or is it just going to keep going? So that's the conceptual approach.
Is it the camera recording?
It is recording. Thank you. Daniel.
I don't wanna sound rude, but how does this, how is this translated into, the stuff, I guess we've done?
Well, I mean,
I guess if it were a problem, how would that work into it?
you have the exact, I mean, you were pulling that from somewhere.
Yeah, from the master set,
Master set, okay.
the 26. The 1, 2, 1, 3, 4.
We have one due on Thursday?
It was, I'm trying to, I know I've done problems with this. So you have, oh. So force, let's just take a look at magnitude of force right now. Magnitude of force is the negative derivative of potential with respect to R, X, whatever it happens to be. So where the force, total force is 0, you are basically at a minimum or a maximum. So the equation, so the problem would be, and again, it's somewhat artificial, but if I have a positive charge here and a positive charge here, where can I put a charge so that it is, so that it's an equilibrium? Well, it's gonna be in the middle, either positive or negative charge. So if I put a positive charge there, this is pushing on it that way, and this is pushing on it that way. So once I have an equilibrium spot, now I need to figure out, is it a local minimum or local maximum? Well, take derivative, this would be the second derivative of u. I'm ignoring the negative sign at the moment. And that should, so if you plug the value of R in, I guess I shouldn't ignore the negative sign. So the all right, I'm going to talk conceptually here because I need to think through the negative sign. So if we take the derivative of f with respect to r, that, and then plug the value of r in, basically we're dealing with the second derivative here. And then that should tell you maximum or minimum, and you didn't have to think through the negative sign. I know in this particular case, conceptually, if I push this positive charge closer to this side, it's going to be repelled more by this one, repelled less by this one, so the net force is back to where it was. So that would be a stable equilibrium, that would be the local minimum. If it were negatively charged and I pushed it, suddenly this attraction is stronger than this attraction, and so it'll keep going, so that's unstable, so that should be a local maximum. And then I'll justify the minus sign afterwards once I've done that. That's basically my approach there.
Yeah.
Was that too general for you?
No, I understand.
Okay. I don't know why I'm looking at Precious. Any other questions? Okay, Precious.
So, for example, we have, the parallel plates.
Right.
Right, and they did give you the voltage between them. They're asking for you to find the voltage from, the positive to the negative plate.
Right.
And I think they gave you the area and the distance between them.
Right.
So, I know that if, like, what my approach was, the Vex equation, or the VED equation.
Okay, right.
And then, so my electric field was sigma over, epsilon sub naught.
Right.
But sigma is Q over A.
Yes.
So, but what do we plug into Q? Is it the positive, charge or the negative charge?
If it's a parallel plate capacitor, they should be the same magnitude, just one's positive, one's negative. The convention is, you know the electric field goes from positive to negative, but the potential increases when you go from negative to positive. Potential increases opposite the direction of electric fields. So, what you would plug in, typically you plug in the positive value of Q, but you could plug in the negative value of Q, and you're talking about the negative plate now. But it doesn't really matter, as long as if you know the direction of the electric field is from positive to negative, then you can ignore the negative sign of the electric field and just say, oh, it's going that way or that way, whichever way it's drawn, or that way. Is that sufficient?
Yeah.
Okay.
So can I ask one more question?
Yep. Sorry, I keep assuming you're, anyone else besides Precious, or just, she's on a roll.
Ask away.
All right, keep
Um,
going.
so, I think last Tuesday, you graphed the sphere conductor, like the electric field versus R.
Right.
And also the potential versus R.
Right.
What happens if it is a dielectric?
Then, let's assume positively charged just to make life simpler. So I have a dielectric here, assuming with uniform charge distribution. So I've got charge throughout the whole thing. So my electric field, so this is my electric field, this is R. My electric field increases the closer I get until I get to the surface. I know my electric field in the center is 0. I know my electric field, here is not 0. It's not like a conductor where suddenly it just drops off to 0 here. This is actually linear.